Hi, this is Tom again, and we're going to continue with some state space machinery, and we're going to move toward putting some economics in. And I'll kind of tell you the battle plan to plan. So you know what we were doing last time? We had this state space model that we wrote like this. And we had x0, normal, u0, sigma 0. And we had w, the t's, normal, 0i. That was our basic state space model. Everything inside is either a vector or a matrix. Here we're going to actually be going after an economic interpretation of some of the parameters, not all of them, but some of them. So what we're going to do is we're going to have this. We're going to augment this model. I'll kind of give you the big picture that where we're going. We're going to augment this model with like this. We're going to start with this model. A xt plus b, there's a b now, ut plus c wt plus 1. So the a and the c and the wt plus 1 and x, they're all the same. They mean the same thing. But now we have this b and we have this ut, and ut is a decision variable or a control, and it's under the control of some person, a decision maker. And the decision maker, the stripped down version is that the decision maker can move ut around. In particular, it could, for example, set ut equal to some feedback rule. It could use what's called a feedback control. Somehow it could set ut equal to minus fxt, which would affect the dynamics. So if I were the controller and I could move ut around, and again, ut is a vector, b is an n by, let's say, k vector, and ut is a k by 1 vector of controls. Well, then what I could do is, if I set this ut, the system would be, the resulting system would be a minus bf. If I substitute this in here and rearrange, the resulting system would look like this. So by reshaping f, I'm going to change the dynamics of the x system. And the economics here is all about how should I choose x to reshape the dynamics of the system. This is going to be so how should I do it? You have to tell me what I want. So what's typically done is to endow the decision maker with some preferences. And to make the problem kind of tractable, this has been done for 3/4 of a century. To make this tractable, what we're going to say is, here's what I care about. I care about this. Some criterion like this, where R and Q are positive semi-definite matrices, And what I care about is I want to, since they're positive definite, I want to minimize this or maximize, I want to maximize minus this. Beta is a discount factor between 0 and 1, let's say, beta between 0 and 1. This lives in between 0 and 1. I want to maximize this. X0 is given. X0 is given. Something's wrong with this because, well, that randomness, there's randomness. So actually what I want to, I'll take the expected value of this. Because now when I choose B, this is now a random process. There's these probability distributions. Now when I choose this F, I'm shaping those probability distributions, and we know what they look like from the formulas that we did last time. So now what I want to do is I want to choose an F to make this thing as big as possible. So that's a classic control problem. So today I want to drill down and stare at that program, that control problem. And it has a couple of remarkable features, this problem. What we want to know is, what does F depend on? So using our fancy technology, is F is going to turn out to be some function. It's going to depend on, well, it's going to depend on A. This is going to be a theme in this class. It's going to depend on A. Now it depends on B. It depends on beta, the discount factor. It depends on these two return or cost, whatever they are. It depends on R and Q. So this decision rule is going to respond to, what I care about, the objective, and the constraints, A, B. So we actually kind of want a formula for how F depends on those things. That's and that our economics is going to be loaded in through that. So where we're going to go is we're going to we study this problem in kind of steps. And I'll tell you a few things about these problems and set up some things I want you to read about it. And this problem has, it's been a workhorse in a whole bunch of applied fields, including economics. So, and it'll get us quickly into the economic structure of some problems we want to study. That's where we're going. Okay, so I'm going to attack this problem by kind of simplifying it first. Hopefully not oversimplifying, but I'm going to simplify it and then I'm going to unleash put some more complications in, but you're going to see the complications don't really matter. And I want to investigate that. That's what I want to study with you. Okay, so let's write down our problem again. Here's the problem. I'm going to set beta equal to 1, so beta is going to be out there. The criterion is I'm going to set beta equal to 1, and I'm going to set C equal to 0. So I'm going to turn off randomness. So the probability distributions are going to be trivial because my covariance measures are all going to be 0. So all that's going to be mattering is going to be the means, and they're going to be trivial random variable with no variations at every point in time. So we're going to do the deterministic thing, and then we'll add the randomness back, and it'll turn out there's a beautiful thing about this problem that we can get a long way for the problem with randomness in by first studying the problem with randomness out. A very famous economist saw this. Some very famous economists. Names were John Muth, Herbert Simon, and the great econometrician Tile. So I'm following in their footsteps here. So there's going to be this criterion function that's a transpose. And then my law of motion now is going to be this. Given. So what I want to do is I want to, this is my objective function. Here's my objective function. And here's my constraint set. How many constraints are there? There's t equals 0, 1, 2. And I'm going to, I want to maximize this by choosing a sequence of a huge number of things. I want to maximize this by choosing a sequence of control vectors and next period state variables subject to this sequence of constraints. And I want to maximize this or minimize, there's a minus there, minimize the sum of these two quadratic forms. That's my problem. That's called the undiscounted linear quadratic control problem. And I forgot to tell you, I want this sum to go from 0 to infinity. And it could be, just warn you, this could be a very nasty problem. It could be so nasty that there's no solution to it. That the solution is the maximum value. It could easily be that the maximum value of this thing is negative infinity. That's the best you could do, which is a disaster. And there's going to have to be some conditions on A and B, and maybe even R and Q, that keep us away from that disastrous possibility. And we're going to see that. So this is a problem where there's, I don't know whether you may think it's simple, or you may think it's kind of complicated. I'm on the camp with complicated because we have an infinite number of constraints, one for each t, and we have a very complicated objective function, infinite horizon objective function. So we have to be kind of cautious. Okay, with that said, we're going to attack this problem in two different ways. One that it's widely used all over applied economics and applied math. And it's going to go like this. We're going to use, we use dynamic programming. This is our first method. And actually, I want to save this here so I don't erase too much. We're going to use dynamic programming. Okay, so here's what, I'm going to kind of give you a little summary of my take on dynamic programming for this problem. It's kind of based on a pretense, or a bluff. We're going to pretend that we've already solved the problem. We're going to start by pretending that we already solved the problem. That's what I mean by pretense. And what I mean by that is, and every time you use dynamic programming, you adopt this pretense. And the way you do it is you start by saying, I'm going to let, I'll call it V of x0, because x0 is being, let V of x0 be the solution of this problem. So I'm going to say v of x0 is equal to what? Equal to this max. V of x is the optimum value of the problem, starting from any x0. You tell me the x0, you vary the x0. V of x0 is the value of what? The value of this objective function maximized subject to these constraints. So I'm going to start that. That's what if you ask me what V0 is, and then I'm going to guess, I'm going to assume, here's another thing, I'm going to assume that V of x0 is equal to minus x0 transpose p x0. I'm going to assume that. So I'm going to assume let that and assume this. So with that, I'm now going to write down, with that assumption, I'm going to write down, see, this is a function. I'm going to write down a functional equation. The internal, if I knew this answer, I'd kind of know how to write down the solution to the problem quickly. There's a big chicken and egg here. But so here's what I'm going to write down. I'll write this down. I'll to save myself some notation, I'm going to write x prime p x minus, that's just, I'm going to drop the x0 subscript, just say x today, is going to equal to the maximum value today of u. I'm just going to be lazy. So what I'm going to do is I'm going to p minus, so that's this term today, and then tomorrow, tomorrow, what's my state tomorrow? Tomorrow my state's going to be ax plus bu, and then I'm going to transpose this, put a p here, ax plus bu. And now what this is that's a transpose. What this is, that's tomorrow's value of x. Because all I'm substituting in is I'm using this equation right here and putting that in there. So x is today's x. Ax plus bu is tomorrow's x. So this is tomorrow's value function. And so what I'm doing is I'm choosing my control, realizing that when I choose my control, it costs me this, but it gets me this tomorrow. So I've broken the problem into today and then tomorrow. And tomorrow the idea is I'm going to be in the same situation I am today, but just with a different state. Instead of x, I'm going to be in the state ax plus bu tomorrow. So this thing is called Bellman's equation. It's a functional equation, and it's got if I know p, I would be able to figure out, if I know p, but I assumed that I knew p's. Okay, so pretending that I know P, this is just a linear algebra problem. And if I solve it, I use 3 lines of linear algebra. And what I'll find out is that U is equal to, I'll let you do this. I'll let you do this on your own. You don't want to watch me doing this kind of linear algebra. If you could take the first order conditions for this problem, using a couple of rules from linear algebra, which will be in the notes that I'll give you, you'll find that U is equal to minus Q plus, it's a famous formula, B prime P B inverse B prime P X. And this thing is just, that's kind of a formula that I promised you. That's equal to minus F times X, where this whole baby is a matrix F. So this is telling me what my optimal feedback rule is as a function of B, P, and Q. And this all pretends that I know P. Now here's the magic thing. Here's the magic thing. If I now, you don't want to do this linear algebra, and now what I do is the following. I'm almost done. The logic's going to be this. Well, wait a minute. I now know that U is equal to minus this thing times X. So I could substitute my big, long, fancy formula for U in here, substitute it in, and do all this multiplication, and then stare at it. And if I stared at it, I'd get a big, long and I'll do the same thing here. I'll also substitute in here, 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 and here. I'm going to substitute in my big formula for U. What's my formula here? I'm going to do that, substitute in, do 3 lines of linear algebra, and I'm going to stare at it. And if I stare at it, I'm going to end up getting this formula. It's a very famous formula. Let's get ourselves a little bit of room here. We'll just take that F out. That's my formula. Now, it's got a name. It's got a name. It's called a matrix Riccati equation. You could look that up on Wikipedia. Okay. So let's go through our logic again. Just on this little board, these are the key formulas for the linear quadratic dynamic programming problem in the undiscounted case. And the key formulas are, here's our formula for U, that's our formula for F, and here's the formula for P. Now you could say, wait a minute. Here's P on the left, and P's on the right. So, and what is P? P is an n by n matrix. And the same matrix is appearing on the left and the right. So that should cause you to hesitate. And then the second thing is, what you might say is, this is what I'd do. I'd say, being naturally suspicious, I'd say, wait a minute. Let's just do this for a scalar case. Let's have n equals 1. Let's have n equals 1. Well, in that case, that's a scalar. But if you stared at this equation, you'd see the right-hand side's kind of a quadratic in P. Quadratic in P. So, well, wait, quadratic P, it's a quadratic equation. There's going to be 2 solutions. Okay, yeah, and you only want 1. Then the other thing is, say, well, wait a minute. If it's not the scalar case, P is an n by n matrix, how many solutions are there? Well, there's a lot. There's a lot of them. And now you can say, which one should I want? Okay. So it turns out some economic reasoning is going to come to our rescue, because almost all of the P's that you solve for are terrible. If you put P's that solve this equation, you could put P's that solve this equation. This is a fact that everyone knows, but they kind of don't mention it. And you'll see why they don't mention it. You take a P that solves this equation, compute this F, and put it in here, it's a disaster. It'll typically be a disaster. I mean, this thing will go arbitrarily small. I mean, it'll be negative infinity. Okay. For most of them, these P's are terrible. Okay. But guess what? There's an algorithm that's kind of guaranteed to get a P that's the unique one that you really want. So let me tell you the condition, what it is. So I'm going to tell you how this algorithm goes. And it's built into dynamic programming. So we can use some of our, I'll tell you the algorithm. Here's the algorithm. And here's what the algorithm assumes. It assumes something like this. This algorithm is guaranteed to work under the following conditions. We're going to assume that R and Q are, by that I mean they're positive definite matrices. They're both positive definite matrices. Okay. So basically under those conditions, if you do the following algorithm, on the right-hand side, every place I see a J, I'm going to put a P, I'm going to put a G, every place I put a P, I'm going to put a J underneath. J's for iteration number. And on the left-hand side, I'm going to put a J plus 1. And what I'm going to do is I'm going to set P0 equal to 0. I could actually set it equal to any positive semi-definite matrix. So I'm going to set P's, I'm going to choose some initial condition, and now I'm going to start iterating on this. That's called iterating on the Riccati equation or iterating on the Bellman equation. I'm just going to iterate on this, and trust me, it's going to converge. And it's going to converge to a unique fixed point if you do it this way, only one fixed point. It's going to converge to one of the solutions of that equation without the J's in it that I told you about. And it's the right one. It's the one you want. So this is actually how you compute the P. Once you compute the P, you iterate to convergence on this thing. Successive iteration. It also turns out to be a backward induction. I'll give you something to read about that. It's a backward induction. So that's what you do. And then you put that in here, and then that's your F. And this is how you solve this problem. Okay. So just with this, that's the undiscounted, non-stochastic, linear quadratic dynamic programming problem. It's a workhorse. Now let me tell you, what I'm now going to do is I'm going to tell you about a really important result, and it's going to play a role in things we're going to do down the line occasionally, depending on what we get to. That's kind of a remarkable thing. So this is the add-on. So right here, we saved some room inadvertently. I'm now going to do the other case, and I'm going to tell you a result. I'll tell you where you can read about this, but I'll tell you the result. It's important to understand the result before you know. The result is this. I'm going to now solve exactly the same problem, but I'm going to have beta equal 1. It's not hard to change that. If beta weren't 1 in this problem, there'd be a beta here. There'd be a beta right here. And as a consequence, there'd be a beta here and a beta here, and there'd be a bunch of betas here. There'd just be some betas tacked on. But basic logic would go through. Well, I'll stick beta equal to 1. But now I'm going to set C can be whatever you want. It's not equal to 0. So now I'm going to give you the key finding, and this has been used widely. It has a name. Tile, the great economist Tile and Herbert Simon called this certainty equivalence. John Muth used it a lot. The result is going to be V optimum is going to now be minus x prime p x plus d. And the decision rule is going to be u equals minus f x. The p and the f are going to be exactly the same as if c were 0. When I turn on c not equal to 0, it's not going to affect p. It's not going to affect f. It will affect a constant term d. It will add a constant to the value function. And that's all. But it will not affect the decision rule. So it'll affect it's a remarkable thing. As I turn up the volatility of the shocks, it's going to lower the value function. But it won't alter the curvature of the value function, and it won't alter the decision rule. So this is called certainty equivalence. And how do you prove this? It's actually easy. The way you prove it is you include C at this step with the relevant expectations. You do the math, and you find that C has no impact on this marginal condition. That's the way it works. Okay. So that's the dynamic programming formulation of this problem. And then I can kind of show you like how we delivered something. We delivered on a promise I made at the beginning. So let me tell you what that promise is. So I think I can erase all this. I'm going to give you some things to read about this. So now let me tell you how I delivered on this. that we promised. What did we promise? When we're done with this, we have, here was our model. We've delivered on a lot very fast. Now, I've skipped steps and told you to go read some things, but I'll give you what to read. So I'm kind of giving you a reader's guide of that. We started with this. I can actually tell you, I can actually take advantage of this and kind of tell you the punchline. I told you the optimum rule now is ut equals minus f xt. So that means that our ultimate law of motion is now not a0 but a0 twiddle xt plus c wt plus 1. Where what's a twiddle? A twiddle is equal to a minus b f, where f is given by that formula I gave you. F is that function, you know, it's a function of a, b, q, r, but not c. Depends on the specification of preferences in the dynamics. So now if I change, if I have this rich thing, if I have an economic agent like a consumer or an investor, this model used all over the place to model consuming under uncertainty, and we will use it that way. Investment under uncertainty. This is going to tell us how we change, if we change these parameters, it'll affect the stochastic process for the state in this way. But now, how will it affect the joint distribution, you know, that I said we were after? The joint distribution, how's it going to affect the joint distribution of xt, xt minus 1, xt minus 2, x0? Well, through the formulas that we did an hour ago. So kind of we have a machinery that tells us how, now we're kind of creeping up on a, what I called earlier was a structural model. This is kind of linear quadratic structural econometrics. And this is the heart of how we do it with those formulas. Because I gave you those formulas for the marginal distributions. Okay. So that's kind of how this fits together. And notice here how I'm using the certainty equivalence here, because I got my formulas for F, and C is not here. Not C. I used that here. Okay. So there's a lot to digest here. We've kind of broken it into steps. Okay. So now I'm going to do the same thing in another way. I'll tell you what I mean by that. Because get rid of this. And now I'm going to get rid of this. Oops. Okay. And I'm going to go back to our original problem, and I've turned off the randomness with C equals 0 to go back to the original problem. And now I'm going I'm going to attack this problem pretending that I don't know anything about dynamic programming. I never saw dynamic programming. But I've had a good micro class, which I remember, and I remember about Lagrange multipliers. And I know how to solve constrained optimization problems. So here's what I'm going to do. I'm going to I'm going to stare at this problem. I'm going to cross my fingers and hope that infinity, well, I'm going to hope infinity doesn't get in the way here. And, you know, if nature's kind to us, maybe it won't. Sometimes it does, infinity. So I'm going to stare at this problem. And then what I'm going to do is, I can actually eliminate one of our lines here. Might be too greedy here. Okay, what I'm going to do, good. What I'm going to do is I'm going to stare right here. For every one of these constraints, I'm going to put a Lagrange multiplier on that constraint. And then I'm going to form a Lagrangian. And because I'm lazy, the multiplier I'm going to put on here, it's going to be a vector of multipliers. I'm going to put the multiplier, I'm going to put a multiplier mu2, mu t plus 1, 2 mu t plus 1 on this constraint. And I'm going to form a Lagrangian. And then I'm going to get the first order conditions. So my Lagrangian is going to look like this. It's going to be a minus. I just copy this. There's my Lagrangian. I got to transpose it. And here's my constraint. A xt plus b ut minus xt plus 1. It's my big Lagrangian. So that's my multiplier on this constraint, just as I promised, okay? Well, there it is. And now, what am I going to do? I'm going to take first order conditions, and I'm going to take my first order conditions I'm going to maximize. What am I going to do? I'm going to maximize with respect to the UTs. I'm going to have a huge number. I'm going to maximize with respect to everything, all of that stuff. And I'm going to minimize with respect to Lagrange multipliers. Minimizing with respect to Lagrange multipliers is just going to recover the constraints, as it always does. So I won't write, well, I will write those down eventually. Okay. So if I do that, here's what I get. I get these constraints. I get 2q. I'm just using linear algebra formulas for differentiating quadratic and linear forms. They'll be in the notes that I tell you. I get these and this is for t greater than or equal to 0. And I get this one, mu t These equations have an interesting structure. Okay. And then if I actually let mu 0 be a shadow price with respect to x0, in other words, I add a shadow price with respect to this constraint, x01, I get an additional constraint. I get, if I add that, I would get this constraint would be greater than equal to, I would get this greater than equal to 0. There's an additional, I'm going to put a Lagrange multiplier on that constraint. Okay. Okay, so now what I'm going to do is I'm going to rearrange these equations. See, I can take these equations and I can rearrange them. Okay, so I can rearrange those equations, and I'm also going to use what I'm going to do is I'm going to take this equation and solve for ut as a function of mu t plus 1, and then I'm going to substitute the result into this equation here. So I'm going to take, I can solve this equation for ut as a function of mu t plus 1 and substitute the result into this equation and rearrange it. And if I did that, and did some rewriting, I would get the following equation. So again, what I'm doing, substitute this as a function. I'm going to solve this for ut, just straight linear algebra as a function of this. Substitute this, rearrange, and I'll get this equation. Big matrix M. This is a 2 by 2 matrix. No, this is a 2. The dimensions are, I have to tell you, this is a humongous matrix. I'll tell you the dimension. That's times xt ut. Where this is an n by 1 vector, and this is an n by 1 vector. So this whole thing is 2n by 2n vector. And this is a 2n by 2n vector, a matrix. That's what M is. This is a big system. And now that's when we did this differentiation and we got the first order conditions for our problem, we arrived at this system. Okay. So now I'm going to Now we're going to stare at this equation. We're just going to study this for a while. So let me tell you what we're doing. And just back up here and just kind of talking to myself. I have to relax at this stage. What am I doing? Here's the problem we want to solve. Everything we want to solve is here. And remember, we already solved this problem. We solved this problem with dynamic programming. We solved this problem with dynamic programming. We computed the optimal u as a function of x, and so on. We got the value function. It was equal to minus, remember, we verified that our guess That's what we did with dynamic programming is a big guess and verify. Okay, so we verified that. So we already solved it once, and now we forgot that we solved it. That's when I started with this fancy line here. And we're doing it again using undergraduate methods with Lagrange multipliers. Okay, so I get my first order conditions, I do a little linear algebra, I rearrange, I get this equation. Okay, and get this equation, and now a couple things I'll tell you about this equation. First thing to note is, well, it's a difference equation. It maps xt mu t into xt plus 1 mu t plus 1. Mu t is the Lagrange multiplier, and it has a state. If xt is called the state, what some people call mu t is the costate. That's the costate. Okay. So now here's something we run into a problem. X0 is an initial condition. We want to know what's the initial condition for here. Well, X0 is a given initial condition. Well, we need an initial condition for mu 0. But we don't have it. Because mu 0 is something we want to solve for. So now this looks like a dead end. Because we did our stuff here. We wrote down all the first order conditions. And we ended up with this. And we'd be done if we knew mu 0. Because we have this m, in the notes I'll give you, m is just a function of all the parameters. Turns out to be a matrix that's pretty interesting. I'll tell you a few things about the matrix in a minute. Okay. And this is related to something we talked about earlier. Okay. So we need an initial condition for mu 0. Okay. And kind of like, why do we need that? Well, if we had that initial condition for mu 0, remember, we solved this equation for ut as a function of the mu's. If we knew what that is, we would have our formula for ut. So we needed to find out what our control law is. Okay. So now here's kind of the problem. If you stare at this matrix, it turns out it has a property. It comes from physics. The property is that M is called a symplectic matrix. Turns out, if you check, it's in the notes, it's called a symplectic matrix. Okay. It occurs commonly with people using Lagrangians. Okay. Turns out that this matrix, it has eigenvalues that occur in reciprocal pairs. If lambda is an eigenvalue, so is lambda inverse. So that means if 0.5 is an eigenvalue, then 1 over 0.5 is an eigenvalue. So it flips. Okay, so it's going to turn out that because half of the eigenvalues of this M are greater than 1, this is an explosive dynamic system. And it's going to go off to, it's going to explode to plus or minus infinity for almost any initial condition. And if it explodes to plus or minus infinity, these x's are going to go to plus or minus infinity. So that means that this quadratic form is going to go to plus infinity at a very fast rate. There's a minus sign. It's going to be a disaster. So almost any mu 0 is going to lead to an explosion in the x and the mu. It's going to be a horrible solution. But it turns out there's going to be one mu. I'm going to tell you what it is. There's going to be one mu 0 that prevents explosion and leads to nice, stable x's. And the mu 0 that does it is px0. It's px0. Okay, so what's P? What's P? Guess what? That P is the same as the P up here. That P is the P that we got from dynamic programming. And furthermore, we could compute this P by carefully analyzing this M matrix. So it turns out, even though when we formulated this Lagrangian, and we didn't have this value function from the beginning, it was there. It was lurking. And it enters right here. So it turns out this mathematics that I've shown you, it's at the heart of a whole bunch of analytic techniques that are used. It's at the heart of something that's used in what's called new Keynesian models that are using all over the place. There's an equation like this, and there's an equation like this that's used there. So I think well, we covered a lot of material. It's kind of a reader's guide. I'm going to give you some readings on this, and I think if you look at this and then look at the readings, you'll see the what we're doing. So what do? We attack this problem in two ways. One with dynamic programming, and then one with Lagrangians, and they fit together like hands and gloves. And thanks for listening. We're going to have a lot more fun with this.